Hi, and welcome to this section of the Matrix Algebra Tutor. And in this section, we're going to build upon what we've laid the foundation of in the last section, talking about matrices and the elements of a matrix and all of that stuff. We're going to continue learning about matrices, and specific in this section, we're going to talk about addition, subtraction, and multiplication of a matrix by a scalar. That's really important because it's a little bit different than multiplying a matrix by a matrix. Multiplying by a scalar just means you multiply the matrix by a number. A scalar is a fancy word that just means a number. That's really all it means. You'll see a lot of times in your book as a scalar multiplication. It just means multiplying by a number. So remember back from your basic algebra when you learned about a negative number. Okay, that was a foreign, crazy concept at first, and you had to learn how to add them. You had to learn how to subtract them. You had to learn how to multiply them. Okay, you had to learn all of those little rules that many of you guys that have been with me for a while learned it in part by watching the DVDs. You had to learn that stuff, and it was not something you were born with. So we're going to study how to add matrices and how to subtract them and how to multiply them by a number. Okay, we're going to go through these operations just like you had to learn the basic operations of your exponents or whatever back before. We're going to lay this foundation so that when you get to the more complicated stuff, it's not going to seem like a big deal. The good news is, and this is really, I do mean this with sincerity, adding and subtracting and multiplying by a scalar by a number really is what that means, is very, very simple with matrices. It's very, very simple. You're not going to have any problem with it at all, okay? The long and short of it is to add two matrices together, they have to have the same number of rows and columns, okay? They have to have the same number of elements, the same number of rows and columns, same order is what it means, same size and shape. And in order to add them or subtract them, all you do is you take the elements, the corresponding elements in the matrices, and you add them or subtract them. That's really all it is. You're looking at the corresponding ones and you're adding and subtracting. Now, your books usually aren't going to phrase it that way. They're going to phrase it in a different way. I'm going to write that down just so when you're reading your book, you won't be lost as to what they're talking about. But that's really all it is. You're looking at the corresponding elements in the exact same positions, and you're adding them or subtracting them. That's how you do addition and subtraction in matrices. So for matrix addition, okay, this is what you need to know. Two matrices of the same order, let me go ahead and underline this right here, can be added. Okay, that's exactly what I said a minute ago. They have to have the same size and shape. Remember, the order is just the number of rows and number of columns, so they have to have the same order, the same number of rows and columns in order to add them. So all you do is you just add corresponding entries. Okay? And the way you're going to see this written in your textbook, in sort of in math language, okay? If you have a matrix that you're representing by the letter A, this letter A represents an entire matrix, okay? And you're adding it to another matrix that you're using to represent by a different letter B. So this is matrix A and matrix B, and you want to add them together. What this says is that they have to have the same order. They have to have the same number of rows and columns. Otherwise, you cannot add them. It cannot be done. Whereas before, you can take any two numbers and add them, you know, from basic math, from first grade math. You can take any number and add it to any other number, no problem. Matrices, not true. You cannot add a matrix this big with a matrix this big. You cannot do it. It does not exist. That's really what it boils down to, okay? They have to have the same order. It means they have to have the same size and shape. And the way they'll write this down in math language is like this. AI sub j plus BI sub j. Now let me explain a little bit the notation so that when you're looking in your book, it's not going to be so foreign. This is matrix A, the elements of which are written as little a, I sub j. This is row and column. This is just like what we were doing before when we're picking out the elements along the row, the ith row and the jth column of matrix A. Matrix B has elements little b, again, I sub j. What this means here, this I sub j plus b I sub j, all it means is this very fancy math language of saying, if I'm looking at the same row and the same column, notice I have I and j here and I and j here. If I'm looking at the same row and the same column, I pick out the same row and the same element in both matrices is what I'm doing. At the ith row and the jth column, at the ith row and the jth column, I'm picking out the exact same element, corresponding element, in both matrices, and I'm adding them together. That's why there's an I and a J and an I and a J. It's basically telling me I have to pull the same element out because it's the ith row in the jth column. Ith row in the jth column. So I go off and I can do that for every single element and add to it the corresponding element in B. And once I do that for every element, then I've arrived at the sum of these two matrices, basically. Now, for subtraction, I'm not going to write all this stuff exactly, over again, exactly the same, because it's really exactly the same. So for matrix subtraction, okay, you just subtract corresponding elements or entries, whatever word you prefer to use, corresponding elements, corresponding entries. It's the same thing as what's going on up here. Matrix A, you want to subtract from it matrix B. The only way you can do this is if these two matrices have exactly the same number of rows and columns, meaning that they have exactly the same number of elements in exactly the same positions. So you write this as A, little a sub I, j, minus little b sub I, j. Again, all it means is I look at whatever element I'm looking at in matrix A, at the ith row in the jth column. I'm subtracting from it the corresponding element in B at the ith row in the jth column. That's all this means. This is math speak of saying corresponding element from A and B. I look at it and I subtract them, and I do that for every element, and I've arrived at the difference of these two things, okay? So adding and subtracting matrix really is nothing more than adding and subtracting numbers, okay? That's the good news. It's very, very simple. That's why I was telling you. Now, the final thing I want to write down for you before we go ahead and work some problems is if you want to multiply a matrix by a scalar, which again, don't get scared off by the term scalar. A scalar just means a number. Multiply by 1, or multiply a matrix by 2, or multiply it by 5, or whatever. Okay? All you do, you just multiply, in layman's terms, you just multiply each element by the scalar. So again, it's very, very simple. So if you were going to take the matrix A, let's say, and you were going to multiply it by a number, and let's say that number is the number C. It could be any number. It could be 1/2. You could be multiplying this matrix by 10. You could be multiplying it by -5. You can multiply it by pi, whatever. It's just a number. The number is the letter C. We're going to multiply it together. So the number is out in front, just like you were going to multiply 3x. The number's out in front of the variable. So it's just that I'm generalizing it, and I'm saying the letter C is the scalar you're multiplying by. All you do is you take every single element and the inside, I sub j, you go through all the elements, rows and columns, and for every one of them, you multiply by the number C. Okay? That's all you do. So when you're multiplying a matrix by a scalar, you look at every single element and you go through, and for every one of them, you multiply by the scalar. It kind of makes sense. To multiply a matrix, you must multiply by every element by something if you're multiplying by a scalar, and so you multiply each element just like this. So adding and subtracting matrices and multiplying by a scalar, very, very simple. You look at the corresponding elements, you do the addition by element, and subtraction element by element. If you're multiplying by a scalar, which is multiplying by a number, you look at every element, you multiply by that number, okay? So in the problems that follow, just to get some experience with this stuff, instead of looking at the math speak over here, what we want to do for all the problems that follow is we want to find the following things. We want to find a plus b, we want to find a minus b, we want to find 4 times the matrix A, and we want to find 5 times A minus 3 times B. So you see, all we have going on here is some addition matrices, some subtraction, multiplying this matrix by a number, which is a scalar, and then of course you're multiplying each matrix here by a number, and then you're also subtracting the results there, okay? So we're just going to work with each one individually. So let's say the matrix A is equal to 1, 3, 3, 4, 5, 6. That's the matrix A, okay? And the matrix B is 2, -1, 3, -2, 0, and 1. So first thing you need to notice right away is these matrices are in fact, they have the same order. So you can add them and subtract them and so on. You can only add and subtract them if they have the same number of elements, the same number of rows, and the same number of columns, basically is what you're looking at. And these matrices do look exactly the same. So in order to add them, it's very simple. You just write your brackets down. You go element by element. This is the corresponding element over here. 1 plus 2 gives me 3. 3 plus -1, or 3 minus 1, gives you the 2. 3 plus 3 gives you 6. 4 minus 2 gives you 2. 5 plus 0 gives you 5. And 6 plus 1 is going to give me 7. So literally, it's nothing magical here. You're going element by element and adding the corresponding element. So you're going element over, and you're just adding them up. So there's not many steps to really show here, but that's exactly what you're doing. So let's go ahead and do the second part. Let's find out. I should have written this down as this is what A plus B is equal to. A plus B, okay? Let's find A minus B. Okay, so again, we're going to start with the matrix A and we're going to subtract the elements off of it from matrix B. So we start up here with the first element. 1 minus 2 gives us -1. So we write that down in that position. 3 minus a -1, 3 minus a -1 is 3 plus 1, which is 4. Okay, 3 minus 3, because we're subtracting, is 0. 4 minus -2, which is the same thing as 4 plus 2, gives you 6. 5 minus 0 gives me 5. 6 minus 1 gives me 5. So at the end of the day, A minus B is -1, 4, 0, 6, 5, and 5. And it's the same thing. I go element by element, subtracting. You just have to be careful with your signs, just like any time in algebra. When you subtract a negative number, you need to make sure and add it. Add the opposite. Subtract the negative number, add the opposite. So just be careful with your signs, but beyond that, it's really nothing more than what you've done before, but subtracting and adding negative and positive numbers. So the next thing we want to find is the number 4 times the matrix A. Okay, positive 4 times the matrix A. And if you look up here, element by element, all you're going to see here is you're going to be taking this matrix and you're going to be multiplying the number 4 by every single element. Okay, you're going to be multiplying the number 4 by every single element. So starting up at the top, 4 times 1 gives you 4. So you put it here. 4 times 3 gives you 12. 4 times 3 gives you 12. 4 times 4 gives you 16. 4 times 5 gives you 20. 4 times 6 gives you 24. So you should get 4, 12, 12, 16, 20, 24. So again, you go element by element. When you multiply by a scalar, you're literally just going and multiplying every single element by the number outside. Now, it's real important for you to remember that you do it this way only when you're multiplying by a number, by a scalar. When you multiply a matrix times a matrix, which we have not done yet, we will not do it until the next section, that's much more involved. But multiplying by numbers is very simple. You just multiply every element by the number, okay? Now, if I wanted to do the last part, which is 5, let me switch colors here just to make it a little bit easier to read. If I wanted to do 5a minus 3b, okay, then just like anything else in life, you need to do the multiplication first, and then you subtract the results. So that we're going to do everything exactly the same as the order of operations from regular old algebra. Okay, so let's multiply by a scalar here. Okay, 5 times a. Every element gets multiplied by 5. 5 times 1 gives me 5. 5 times 3 gives me 15. 5 times 3 gives me 15. 5 times 4 gives me 20. 5 times 5 gives me 25. 5 times 6 gives me 30. That is 5a. And I subtract from it a new matrix over here, which is going to be 3 times b. b is up here. I multiply every element by 3. 3 times 2 gives me 6. 3 times -1 gives me -3. 3 times 3 gives me 9. Okay, and multiplying 3 times -2 gives you -6. Multiplying 3 times 0 gives you 0. Multiplying 3 by 1 gives you 3. So basically you're just going through that matrix element by element and multiplying by the scalar, which is out in front, which is 3. Now you have two matrices and you're subtracting them from each other, and they have the same size and shape, so it's perfectly okay to subtract these things. You're just going to go element by element. Just be careful, because sometimes you're going to be subtracting negative numbers depending on what element you're working on, so just be a little careful with your signs. Okay, so let's go element by element. 5 minus 6, negative 1. 15 minus a negative 3 is the same thing as 15 plus 3, which is 18. 15 minus 9, I think you can be convinced, is 6. 20 minus a negative 6 is the same as 20 plus 6, which is 26. 25 minus 0 is just going to be 25. And then 30 minus 3 is going to be 27. Okay, so that's the answer. Negative 1, 18, 6, 26, 25, 27. So basically you go element by element at the end. So the answer to this, 5a minus 3b. So basically, you're really following the rules of algebra just as before. You're doing multiplication first, which is what we did with these scalar multiplications, and then you do the subtraction at the end. Addition and subtraction of matrices are not a big deal. You go element by element. If you're going to multiply by a scalar, you multiply the elements. And you see in the end we did the subtraction here just fine, because both of these matrices had the same order, same number of rows and columns, so we were able to go ahead and do the subtraction there. Okay, now let's go ahead and work another one. Again, we're going to find a plus b, a minus b, 4a, and 5a minus 3b just to get some practice. So let's say the matrix A in this case is equal to 2, negative 1, negative 4, and 1. Okay? And the matrix B, let's just say for this problem, is going to be equal to negative 5, 3, and negative 1. Okay? Now these matrices may look a little bit weird to you because they only have three rows and one column, but matrices can have any shape, any number of rows and columns. These are called column matrices because they look like a column, and if you see it written across like a row where there's only one row and a whole bunch of columns, that would be called a row matrix. Those are just words. I mean, really it's all the same thing. It has 3 rows and 1 column, and so they have the same number of rows and columns, so you can add them and subtract them all day long. And you just do it element by element. So if you were going to do that, you would say a plus b is equal to, you would go element by element. 2 plus the negative 5, I think you can convince yourself is negative 3. Negative 4 plus the 3 is going to be negative 1. 1 plus the negative 1 is going to be 0. So that's the answer to that matrix right there. Negative 3, negative 1, 0. And if you were going to go a minus b, same thing, element by element. 2 minus negative 5 is the same as 2 plus 5. 2 minus the negative 5, you add the opposite, so 2 plus 5 is going to give you 7. Okay, it's going to give you 7. And then over here, negative 4 minus 3. Negative 4 minus 3 is going to give you negative 7. And then 1 minus the negative 1, you just add the opposite. 1 plus 1 is 2. So you get 7 minus 7 and then 2. And then to continue on down, it really doesn't get any more difficult. If you want to multiply 4 times a, you just take every element and you multiply by the scalar, just like we were doing before. You just multiply by 4. So 2 times 4 gives you 8. Negative 4 times 4 gives you negative 16. 1 times 4 gives you the 4. So that is the answer. 4 times the matrix A, 8, negative 16, and 4. And if you wanted to, let me switch colors to make it a little bit easier to read. If you wanted to do 5a minus 3b, same thing. You do your scalar multiplication first, and then you do the subtraction. So what would 5a be? 5 times every element in a. 5 times 2 gives me 10. 5 times negative 4 gives me negative 20. 5 times 1 gives me 5. And I'm subtracting from that this matrix 3 times b, the scalar 3 times the matrix b. So we multiply this matrix by 3. 3 times negative 5 is negative 15. 3 times 3 gives me 9. 3 times negative 1 gives me negative 3. Okay? And so now I have two matrices, 10, negative 20, and 5. I'm subtracting negative 15, 9, and negative 3, and they have the same number of rows and the same number of columns, so I can subtract them no problem. Okay? So 10 minus the negative 15, going element by element, 10 minus negative 15 is the same as 10 plus 15. so that's 25. Negative 20 minus 9 gives me negative 29. And 5 minus the negative 3, add the opposite, 5 plus 3 gives you 8. So 25, negative 29, and 8. That would be the answer if you were trying to do 5a minus 3b. So again, do the multiplication first, get that done, and then double check that you can do the subtraction here just to make sure. In order to do that, you have to have the same number of elements, same number of rows, columns, and you just go element by element doing the addition or subtraction as needed. Okay, now for the next problem, let's say the matrix A was given by this thing here, square root of 8, 1, 2, 0. Okay, and matrix B was given by square root of 2, negative 1, negative 3, and 6. Okay, so again, don't get upset because there's a square root in there. I mean, those are just numbers. The square root of 8 is a number. The square root of 2 is a number. These are just numbers in here. There's nothing more to it than that. And so if you were going to do A plus B, what would it look like? Okay, what would it look like? Well, you go element by element. Square root of 8 plus the square root of 2. Square root of 8 plus the square root of 2. Okay, so really there's nothing I really want to do differently with that right now. I'm just going to write it down. There's a little bit of simplification you can do here. We'll do that in just a second, but for right now, let's write it down as square root of 8 plus square root of 2 because that's what we're doing. Going to the next element, 1 plus the negative 1 is just going to give me 0. Over here, 2 plus negative 3 is going to give me negative 1 for that element. And then 0 plus 6 is going to give you 6. Okay? So that's really the answer, and that's probably pretty sufficient to go ahead and do. But if you just wanted to be a little bit more rigorous about it, you could simplify this a little bit, and you could realize that square root of 8, okay, if you remember how to simplify that, 8 is equal to 2 times 4, and 4 is equal to 2 times 2. So because it's a square root, I'm looking for pairs of 2. So this 2 can come out, okay? And what you're going to end up having is this 2 comes out, and this square root of 2 is left on the inside. If that looks foreign to you, then you should probably go back to my Algebra 2 tutor and review radicals and how to do this. There's tons of examples in there. Basically, you write down a little tree, and because I'm looking for pairs, this 2 comes out because it's a square root. I'm looking for pairs here, so the 2 comes out. This 2 stays in under the radical. So this square root of 8 is precisely equal to 2 times the square root of 2. So I can write this as 2 times the square root of 2 plus 2. That's still the same element. I haven't done much with it yet. I'm just simplifying it. 0, negative 1, and 6. And I think you'll see why I did that here in just a second when we complete the simplification. The reason I did that is because now when I write it that way, 2 times the square root of 2 plus, actually this should be the square root of 2, okay? From here, square root of 2. Because this is 2 times the square root of 2 plus the square root of 2, that's just 3 times the square root of 2. If that looks foreign to you, what does the following look like? 2x plus x. Okay, I think you remember from Algebra 1, that's just 3x. You just add the coefficients, right? This square root of 2 is the common factor here. It behaves like the x did here. So because I have 2 of these things called square root of 2, and another one of these things over here called square root of 2, I add them together, I have a total of 3 of these things called square root of 2. So 3 times that thing called the square root of 2. So 3 times the square root of 2. That's why I wrote this like this, so I could add them together. And then finally I have 0, and then negative 1, and then 6. And that's the answer there. So that's what A plus B would look like. Okay? 3 times the square root of 2, 0, negative 1, and 6. Okay? So that's what that would look like. Okay, now if I wanted to do A minus B, it's going to be exactly the same procedure. I'm going to go element by element. So here I'm going to have square root of 8 subtracting square root of 2. 1 minus a negative 1 is going to be adding the opposite. 1 plus 1 gives you 2. 2 minus the negative 3 is adding the opposite. 2 plus 3 gives you 5. 0 minus 6 gives you negative 6. Okay, now remember from the previous problem that this can be written as 2 times the square root of 2. Now, of course, we're going to subtract off the square root of 2 that we had. And we have 2 here, 5, and negative 6. Okay? And again, we did it that way so that we could then subtract these things. 2 times the square root of 2 minus another square root of 2 is just going to give you one of these things called a square root of 2. And then you have a 2 and a 5 and a negative 6. And that rounds out the matrix. Basically, you're just going element by element. You're doing your subtraction. The only thing here is because of radical, I mean, you have to do a little simplification so that you can actually subtract them. Okay, now if you wanted to do part C, which is 4 times the matrix A, it's the same thing as before. You go back and you're looking at the matrix A and you multiply every element times 4. So it's going to be 4 times the square root of 8. 4 times 1 gives me 4. 4 times 2 gives me 8. 4 times 0 gives me 0. But remember that this square root of 8 can be written as 2 times the square root of 2. That's exactly what it's equivalent to. And so you have a 4 and an 8 and a 0. And so finally you just complete things by doing this multiplication. So you'll have 8 times the square root of 2, and then the other elements just stay the same. And this is 4 times A. 8 times the square root of 2, 4, 8, 0. Those are the elements of that matrix right there. Okay, and for the grand finale, so to speak, if you have 5 times A minus 3 times B, same thing as before. We multiply the matrices by the scalars, and then we do the subtraction at the end. So we have 5A. Every element gets multiplied by 5. So 5 times the square root of 8 here. 5 times 1 gives me 5. 5 times 2 gives me 10. 5 times 0 gives me 0. And I'm subtracting from that another matrix, 3 times B, here. So going element by element, 3 times the square root of 2 is just 3 times the square root of 2. 3 times negative 1 gives me negative 3. 3 times negative 3 gives me positive, I should say negative. 3 times negative 3 gives me negative 9. And 3 times 6 gives me 18. So what we have here is two matrices that are multiplied, each one of them is multiplied by a scalar. And then basically what we're going to do is subtract those out in the end. Okay, so all we have to do now is continue to simplify this stuff, and then we'll go ahead and subtract the two matrices here. Okay? What we have here is 5 times the square root of 8, but we remember from before this is 2 times the square root of 2. The other elements just stay exactly the same. I'm not doing anything to them, and in fact in this matrix I'm not even going to do anything to them either. I'm just doing that one step there. Because with radicals, if you do too many things at once, you're probably just going to confuse yourself. So what you have here, the 5 times 2 gives you 10 times the square root of 2. Here you have 5, 10, and 0. Subtracting from it, this matrix, I haven't touched it in quite a while. I'm just writing it down. Okay? Now, after doing the scalar multiplication, we have two matrices that have exactly the same size and shape, so we can go element by element and do the subtraction, no problem. Okay? So starting with this element minus this one. 10 times the square root of 2 minus 3 times the square root of 2. Basically, you're just subtracting the coefficients because the common term is the square root of 2. 10 minus 3 gives me 7 square root of 2. This element, 5 minus a negative 3, is like adding 5 plus 3. You add the opposite. So you're going to get 8. 10 minus negative 9 is the same as adding 10 plus 9. So you'll get 19. And then 0 minus 18 obviously is going to be negative 18. Okay, so if you were doing 5a minus 3b, you would get the matrix that looks like that. 7 square root of 2, 8, 19, and negative 18. So it's the same thing as before. You do the multiplication first, you get that simplified down as far as you can. You know, and if you just left it up here at this point, you know, it would be difficult to move any farther, but then when you realize you can simplify this to 2 times the square root of 2, that allows you to actually do the subtraction here, which allows you to simplify the answer. So it's a simplification thing. Anytime you see a radical in there, see if you can beat it into some form that's going to let you do a good simplification. So this section was, again, introducing us to the operations you can do with a matrix, which really aren't a big deal. You can add them and you can subtract them, and you can multiply them by a number. To add them or subtract them, they must have the same size and shape, which means they have to have the same number of rows and columns, which is a short way of saying they have to have the same order, exactly the same order. And so once you prove that that's true, or see that that's true, you just go element by element, and do the subtraction. That's really all you're doing there, okay? And when you multiply by a scalar, you go element by element again and multiply every single element by that scalar, and you get a new matrix. So those are the introduction to the basic operations with a matrix. And again, don't forget why we're doing this, because in the end of the day, what we're going to do with these matrices is we're going to use them to solve systems of equations. And you're going to use these operations to do that. So addition, subtraction, multiplication by a scalar, very, very simple. Next section is going to start to deal with multiplication of a matrix by another matrix. And that's a little bit more complicated, but with some examples in practice, I don't think you're going to have too many problems with that either.